Okay, I'm on a university internet, so please let me know if my videos aren't playing or I perhaps changed the subject and the slide hasn't changed. Cool, so I'm Dani Clode. I'm going to talk to you today about how the body and brain adapt to material change. Tamar Makin's also here. She's going to join us for the Q&A and the panel afterwards as well. So I'm a prosthetic and augmentation designer. So most of my work is multidisciplinary collaboration. So I work with artists, models, engineers, anthropologists, and now most recently neuroscientists to develop work that really explores the future architecture and perception of our bodies. So studying design, I became fascinated with prosthetics as physical objects because they sit in this really unique crossover between kind of tools and body parts and experience. And they're kind of all of these things and none of them at the same time. And not a lot of objects do that. And the more we zoom in and think about the creation and relationships and interactions, the more nuanced and complex these objects get. So for example, the experience and training needed from the prosthetist to sculpt the form of the socket against the body, or the experience over time of the user to extend the function of their arm through using the prosthetic like a tool for a task, or the contact and relationship that develops over time through feeling the pressure of the prosthetic against the arm in the socket as they interact with their environment. So these objects are really complex and they have a lot of layers, but we should expect nothing less when designing for the complexity and nuance of the human body. But when we start to look at the bigger overarching challenges of prosthetic augmentation and assistive technological development, there's one aspect that seems to be left out of the conversation a lot, and that's connection. We need to consider the relationship this object is having with the body and the relationship and impact it's also therefore having on the brain. So first I'm going to talk about the body and then I'm going to move on to the brain. So through my experience, when considering the future framework for these complex objects, we need to focus more on these three design values. So emotional, aesthetic, and physical connection between the wearer and the object, in addition to function and control. So I'm going to use this piece of work I did with the Alternative Limb Project and Kelly Knox to give you some quite extreme examples of what I mean by these design values. So Kelly Knox, aside from being an amazing human being, is a model and disability rights activist. So from the beginning, this brief was really interesting because Kelly is a congenital one-hander, meaning she was born with one hand. So she was born her whole self, and she actually chooses to not wear a prosthetic. So suddenly this object that's usually so saturated in a specific function became open to alternative perspectives and needs for Kelly as an individual, which for her was expression, extension, and connection. And she also had a really complex and challenging relationship with prosthetics growing up, being told to wear an arm to fit in when she already felt like her whole self. So she's certainly not, and she's certainly not the only one with these past experiences. So our first piece together was synchronized, and this was to explore an emotional connection between the wearer and the object. And with this arm, we decided to completely flip the usual order of focus of a prosthetic and show Kelly's actual arm shape, which you can see in the electroplated carbon fiber socket. So the socket that usually completely hides the arm is now celebrating her body shape. So this then slowly transitions into clear layered acrylic pieces that form a one-to-one mirrored recreation of Kelly's right arm, showing this kind of visual connection with the body. Also, when she turns it on, there's a layer in the wrist that ticks in time to her heartbeat and can continue to tick when Kelly's not wearing it, which creates this kind of lasting connection when there's no longer a physical one. So our second piece was materialize, and this was to push the boundaries and challenge the current aesthetics and materiality of prosthetics. So it's divided into two main sections, part skin-like silicone and part mixed materials, which are also interchangeable. So the arm is made up of over 20 different materials, ranging from hand-finished wood, pumice, and cork to 3D printed resins, plastics, and plated bronze. And not only do the interchangeable elements allow for different aesthetics for Kelly to choose from, depending on how she feels, but they also change the texture and weight of the arm. So the skin side of Materialize was expertly crafted by my collaborator, Sophie, and it was to help kind of form this strong visual connection between, visual connection and recognition between Kelly and the object. And this was actually Kelly's favorite arm by far. And she said, and I quote, "I feel like it was part of me, not separate," which was totally unexpected. And this is really awesome coming from someone who actually chooses to not wear a prosthetic in daily life. So our last piece was the vine arm, which is a kind of botanical tentacle flora-fauna hybrid, this kind of physical reactive extension. And with this piece, we really want to push the boundaries of the material concept of what a prosthetic is or can be. So the vine is made up of 26 individual vertebrae that are controlled by 4 pressure sensors embedded in Kelly's shoes, situated above and below her big toes. So the piece is wireless and motor controlled with 3 main parts. So the socket houses the end of Kelly's arm, as well as the motors and batteries. And above that is kind of botanical armored piece that helps to distribute the weight of the vine, and then the vertebrae come out of the end of the socket. And with this piece, we also tied it back to the emotional through constructing the shape of the vine by extending the end of Kelly's biological arm. So the underlying structure is actually from her body, kind of as if she kind of grew it. And the control was very much connected as well, and that she kind of had this proportional control over the vine through the sensors in her shoes. But the main point is that we were changing her physical body and significantly changing the types of interactions she was having with her environment, and ultimately completely changing the way she was moving her biological body in collaboration with the vine. And as I mentioned earlier, Kelly is her whole self, as many congenital individuals feel. So are these objects prosthetics, or are they an augmentation? So to deep dive into augmentation technology, I developed the third thumb, which is a 3D printed thumb extension for your hand controlled by your feet. So I'm just going to play a little video to introduce the thumb and its control and functionality and how people connect with it, and when they get to use it for the first time, how they feel. So there's 2 degrees of freedom, and as you can see, it's quite a flexible 3D print. And the flexibility of the 3D print connected with the proportional control of the sensors really kind of recreates that kind of natural movement of the thumb. And those are the 2 pressure sensors embedded in my shoes. And this was I made sure to video the first time people used it. So it's really, really cool seeing their reactions. And this is like exploring some of the bimanual tasks you can achieve single-handedly. But yeah, it's a pretty great response from people for the first time. So I'll let you watch the rest of the video. So yeah, so the third thumb project was my graduate work from my design products MA at the Royal College of Art. And it started out of my fascination with prosthetics as objects. So I wanted to really understand what it was like to control something extra attached to my body, as well as expand the motor abilities of the hand. So being inspired by the body and looking closer at the structure of our hands, I realized there were kind of no rigid interlocking parts, only material being pushed and pulled very deliberately. So based off this, I started prototyping with flexible 3D printed filament, trying to recreate this kind of uniquely human movement of our thumbs, traditionally a very challenging part of a prosthetic hand design. And after realizing if I wanted to focus on the thumb, I found a spot for it on the hand that seemed to be quite accepted by people. I knew I was dealing with this kind of strong weird factor, but something about the symmetrical positioning seemed to help, as well as the kind of balanced size and angle. So the third thumb recreates 2 main movements of our thumbs, which is flexion, extension, and adduction and abduction. And these are wirelessly controlled by 2 pressure sensors underneath the big toes. And the foot control idea came out of a side research project of mine into alternative body control, but it was mainly because I couldn't get 2 individual muscle sensor control points from my arm without having to move my hand. And I wanted the thumb to be its own controlled entity away from the arm. So I was also inspired by other products like drums, cars, sewing machines, electric guitars, and found that it's really common for us to use the feet to extend or add to the task the hands are doing. So equally, this framework can be applied to augmentation. And when we consider connection, this is going to influence function and control. And this is really interesting from a design and development perspective. But ultimately, when we make these kinds of changes to the body, we need to consider the brain. We need to understand how the brain responds to augmentation, especially when we're looking to change the way we physically use our bodies together with this technology. And all aspects of this framework are relevant to the brain and cognition. So together with Tamar, Makin in the Plasticity Lab, we used my design, the third thumb, as an augmentation model to explore the brain. So our main research question was, does robotic augmentation of the hand impact body representation in the brain? And given a fully occupied motor system in the brain, where do we fit an extra body part? So we trained people for 5 days, and we're looking at their own body representation before and after the 5 days of training with pre and post fMRI scans and behavioral tests. So we also included a control group that wore the thumb for the same amount of time. For the same training, the thumb was just not operational. So as well as the 2 hours of training, participants were also invited to use the thumb outside of the lab, which was really unique for a study like this. And they got to use it at home and feel like it was kind of part of their life for that week. So with the lab plus at home, they had about 4.5 hours of training per day. So the training was made up of a combination of 9 different tasks repeated over the 5 days. So each task creating a different challenge with the thumb for the participant. So some examples are the Jenga task, in which the focus is to use the thumb in collaboration with another finger to pick up multiple blocks and build a tower. The cups task in the middle is about utilizing the thumb to free up the use of the fingers, in this case to remove a marble from a cup with a spoon. And the tapes task is about completely occupying the hand, so the participant only uses the thumb to help them really fine-tune their small motor movements and awareness of the end of the thumb. And as you can see from the week's data, practice makes perfect. We also then added a dual task, so simultaneously whilst building their block tower, they also had to do some simple addition and subtraction. And this was to test the cognitive load of the third thumb and how the cognitive load of the third thumb was having on our participants. But even while multitasking, their performance was not significantly impaired in both early and late stages of learning, so indicating that the thumb does not have a cognitive impact on the working memory. So alongside the training, we also did a coordination task with the participants. So the goal is to move the third thumb and meet the tips of the biological fingers one at a time as instructed. And we measured the number of fingers that people can successfully find within a 1-minute trial for multiple trials across the week. So we found that participants are able to basically control the thumb straight away, but they get even better at coordinating the thumb with their hand movements in a very short time frame. And here you can see a similar task that we ran at the start and the end of the week of training. And we found that people can perform this coordination task, not just with vision, but also while blindfolded. So they really seem to be developing a kind of sense of proprioception of the thumb and can really be aware of the position of the third thumb in relation to their biological fingers. We also are finding an increased embodiment of the third thumb after training. So our embodiment test is in the form of a questionnaire where people have to respond in a range of statements with 3 strongly agree to -3 strongly disagree. So for example, one of the body ownership questions is, it seems like the extra thumb is part of my hand. So we asked the participants to complete the questionnaire after their first interaction with the thumb and after their last day of training. So as you can imagine at the beginning, they tend to disagree with the statements, but after a week, even though it's quite subjective, they seem to be developing ownership over the thumb and either be neutral or quite positive about the statements. So as a designer, I find the shift to positive of the visual-based statements are very interesting. Questions like, it seems like I'm looking directly at my own finger. So starting off around disagree and ending up around slightly agree, which links back to my previous slides about Kelly. So to summarize, I'll say that participants adapt well to using the thumb, not just in the lab, but also in their own daily environment. So they're quite good at controlling it. And what's more, they show a better connection to it. So they feel like it becomes more like part of them. But all the results I've shown you so far indicate how they relate to the thumb and its control and function. Whereas, getting back to the key question for this initial study, how does the thumb impact the user's body representation? And at a first glimpse into this question, we can answer it by looking at how people adapt the way they use their hands in order to take advantage of the thumb extension. So you may have noticed from some of the images where we asked our participants to wear a data glove throughout the training. And this was to really help us track how they were synchronizing across their own fingers whilst working with the thumb. So this is a PCA analysis showing us that the augmented group requires more principal components to explain the same amount of variance than the controls. So they seem to be using more complicated strategies across the fingers to achieve the task together with the thumb. To remember that the controls here are solving the same problems as the augmented group, but the augmented group has been asked to incorporate the thumb into their motor solutions. So in order to extend their motor repertoire, the augmented group is coming up with different solutions to using their own fingers. So we can unpack this by looking at a co-movement coupling across the individual fingers. So this is the control matrix showing the classic codependence between digit 3, 4, and 5, and more independence of 1 and 2. So here we have the augmented matrix, and the effects are really subtle. So we've got a difference matrix here. So across the board, digit 3, 4, and 5, there are more individuated movements when participants are using the hand together with the thumb. So if you think of the function of the thumb, it's designed to help afford a kind of second pinch grip, which can either work with any of the biological fingers, but seems to work really well in a combination of digits 3 or 4 and 5. So this means that the participants are kind of breaking their natural synergies of using 3, 4, and 5 together in order to afford better functionality with the third thumb. And this is more independent use of the biological fingers, this individuation that is breaking the natural synergies. So we weren't seeing in the, sorry, and this more independent use of the biological fingers, the individuation that is breaking the natural synergies, we weren't seeing in the control group. So even though we went through the same training, they went through the same training with the non-moving thumb. So how does this impact the representation of the body and the brain? We'll be looking at the primary motor cortex across the left and right hand areas. So something to note, during the scan, the participants were not wearing the thumb. They were just asked to move their own biological fingers. So we looked at the individual fingers within the hand representation. So the analysis I'm showing you here comes from brain decoding approach, where we look at how the activity pattern elicited by the movement of each finger is different from the others. So this is called representational similarity analysis. And the way you read these graphs is by understanding that each of these points is summarizing the relative representation of one of the fingers to the others. So here you see the biological thumb in red, index finger in yellow, middle finger in green, and so on. So the more similar the representation, the closer the dots are in the graph. So for example, the neighboring fingers on the hand are closer to each other on the graph. So they are more similar to each other in this representational space. So these are the results at baseline. And as you can see, the representation of the left and right hands is pretty similar. So if we're to quantify the overall dissimilarity across the fingers, they'll be quite similar across the hands. So now I'm going to fade out the baseline data and show you the results for both hands after 5 days of training. So let's start with the left hand. So the non-augmented hand. So we find, unsurprisingly, the representation is quite stable in the left hand, so nothing much has changed here. But when we look at the right hand, which is the hand being augmented after a week of training with the third thumb, you can see a subtle shift of the representation of the fingers away from the baseline position and more towards each other. And we're quantifying the distances across individual fingers with a linear mix model, which shows a very subtle but significant reduction of the representational structure in the right hand relative to the left hand after training. So there's a subtle collapsing of the representation of the hand. I should also note we did do a post fMRI a week later, meaning that the participants were no longer using the thumb at all. And after this rest period, the finger maps were no longer significantly different from baseline. So we think they are returning to their pre-training positions. So just to sum up, a fully occupied brain can support new body parts, but there may be consequences for this representation. This is very much just the start of this research into augmentation in the brain, and we're really excited to continue this multidisciplinary collaboration because we think it's really important to replicate and extend these first findings. So in conclusion, I hope I've shown you today that we can't explore function independently of control, just as we can't explore control and function independently of connection. And I found that to be true and valid both when I consider design aspects, but also when we consider the neurocognitive elements that ultimately can determine the success of the design. For example, our embodiment results have shown that people can create a connection with something they've never had before, like an extra thumb, but the connection and control considerations of using an extra thumb will directly impact control and functional considerations of the biological body, showing that this is a complex puzzle where each moving piece will trigger an effect on the others, and we have to consider all of them in a holistic approach when designing for the future body. Thanks for having me. I want to say a big thank you to our awesome lab members and supporters, and in particular, Paulina Kaliba, who led the science of the study I've shown you.
Thank you, Dani, for this very nice talk. It was beautiful exploring with you the robotics from a different perspective, the one of a designer.
Yes.
So, thanks a lot. I have here one question for you. Xiaoping Bai is asking, what type of sensors are you used to detect figure and arm motion?
Detect the, sorry.
Detect figure and arm motion. I don't know exactly which figures.
The finger for the cyber glove then, or are you talking about the science or how the thumb works? Sorry, there's lots of sensors involved.
Okay, so
we measure the fingers in the study with a cyber glove, which I believe is flex sensors, and then I use pressure sensors to control the thumb with underneath the feet. Yeah.
Okay. So thanks. I have a small question for you. It's just a curiosity. You talked about these three main categories, important categories when you design a new tool, a new device. There was emotional, aesthetic, and physical, if I remember well. And I'm quite curious about what is the most important ones that you consider at the beginning of a design process. I mean, just a curiosity.
Oh, that's a hard question. They should all be influence each other, which I hope I kind of tried to convey. But I mean, it depends on really the focus. My design is very human focused as well, so it depends on what the ultimate goal was. And you can see kind of out of the three arms, they are kind of the first one being a bit more heavily on the emotional side, but still also aesthetic as well. But yeah, they kind of always battle a bit between those three aspects, definitely depending on the brief.
Thanks. Thanks. It's very interesting, this approach.
Yeah.
It's completely different from.
Can I ask a question?
Yes, of course.
Yeah. Hi, Dani. It was really great work. It's really nice designs. Actually, I've seen your design for a long time ago on YouTube. I think when you first put up, and I got to know it from Imperial College, Etienne, and I think you met him as well. Anyway, but really nice work. I just had one question about your last comment. You said that you took some MRI activity after a few weeks. When they stopped work using the finger.
Yes.
Did you also take some behavioral synergy measures at that time? Or do those also come back to the normal levels, or do they remain the same?
No, I have Tamar here as well. So she's in my ear about the neurosciences, because I'm not a neuroscience scientist, obviously.
Of course, yeah.
But no, it was just the fMRI.
It was just the MRI. I see. Okay. I was just curious. Okay. Thank you.
Okay, so thanks again, Dani. It was very interesting.